Welcome to Statistics. Today is Tuesday, April 7th, and we're going to talk about realistic inference today. By realistic inference, we mean inference in which we don't assume that the population standard deviation is known. We have been making that assumption up to now just to make the discussion a little more simple, but we really need to face the realistic situation where the population standard deviation is unknown. Because, after all, if you think about it, if the population standard deviation sigma were known, then why wouldn't you be able to know the population mean mu as well? The situation that you face in practice is the one in which both mu and sigma are unknown. So, how do we modify the procedures that we've been discussing up to now to take this into account? Well, the answer is it's not too difficult. There are some changes that kind of ripple through, but there's a couple of basic ideas that make this very much like the situation we were in previously when sigma was known, with just a few changes. So let's take a look. When we're doing realistic inference about a population mean, the procedures that we're using require that certain assumptions be valid. These are called the conditions for inference. The most important is that the data come from a simple random sample of the population. And this goes back to all the discussion we had back in chapters 8 and 9 on sampling and experiments. This avoids systematic bias in the data we're using. The second assumption is that the population variable x has a normal distribution. And again, here we're going to go ahead and assume that both mu and sigma, the mean and standard deviation of that normal distribution, are unknown. We'll be able to relax this assumption of a normal distribution as well going forward, but for right now, we'll just take things one step at a time. The population variable has a normal distribution, but the mean and the standard deviation of that distribution are unknown. So the basic idea is going to be to estimate the mean and the standard deviation from sample data. We've already discussed how x bar is an estimate for the mean mu, but we can use the sample standard deviation s as an estimate for sigma, the population standard deviation. And then that ripples through into estimates for the standard deviation of x bar. You remember that from the central limit theorem, sigma over root n is the standard deviation of x bar. Our estimate for that will just be s over root n. And we give this guy a special name. We call him the standard error of x bar, in contrast to the standard deviation of x bar, just to keep in mind the idea that the standard error of x bar is an estimate for the standard deviation of x bar. So the standard error of x bar is s over root n, where s is the sample standard deviation, n is the sample size, and the standard error of x bar is an estimate for the standard deviation of x bar. The test statistic then replaces, here's the old test statistic in the bottom here, z statistic, just the z-score for x bar. We no longer have sigma of x bar if sigma is unknown, but we replace it by its estimate, the standard error of x bar. And so we call this guy, we don't call him a z-score any longer because we're using this estimate. But we call him a t-score, and the way you should think about it is the t-score is an estimate for the z-score of x bar. So you interpret it in the same way. We'll see some examples of this going forward. Let's take a look at an example, in fact, right now. We actually looked at this example before. We have a cereal that advertises on the box 12.8 net ounces of product in the box. But a sample of 10 of these cereal boxes were weighed very carefully, and we get these values here for the weight of cereals in each box. So notice that I'm not going to make any assumptions about the standard deviation of the population at all here. Let's check to see if our data satisfy those conditions for inference, and then let's find the standard error of x bar from the data. So, of course, the data do come from an SRS that's given to us. The second condition for inference is that the data come from a normal distribution. Is that the case here? Well, I made a little stem plot of the data. Here it is. The stem plot I've drawn horizontally rather than vertically, but the first 4 decimal places of the weight are the stems, and then the last decimal place is the leaf. So this actually looks quite a bit more like a histogram when you draw a stem plot this way, horizontally. And there you see the distribution of our sample data. Now, does that look normal to you? Doesn't look really normal to me either. It's got a long left tail, and it's got a clump of data right around to the 12.85 ounce area. This shows one of the real problems of doing statistical inference with small data sets. With a small data set, it's really hard to make a definitive judgment about whether the data come from a normal distribution or not. I mean, if we had 100 cereal boxes, then we could make a better judgment. If we had 100 cereal boxes and the curve still looked like the red dotted line, we could say pretty definitely this does not look like a normal distribution. But with just 10 boxes, you know, it wouldn't be that unusual to get 3 measurements out here in the left tail like we've got. So it looks like it may be questionable about the normality of the data, but let's go ahead and perform our inference procedures anyway, with just a caveat that if this data really isn't normal, then our inference procedures may be less than perfectly accurate. So the sample statistics of the data, the sample size is 10. The mean of those 10 values is 12.8399, and the standard deviation is 0.02584. I'm using 4 significant places of accuracy, so I ignore leading zeros after the decimal point here and keep 4 places after the last leading zero. So to compute the standard error, that's just your sample standard deviation divided by the square root of the sample size. So that would be our 0.02584 divided by radical 10. You just grind that out on a calculator. It turns out to be 0.008171. So what we're saying here is that we estimate that sample averages of size 10 will vary with a standard deviation of about 0.008, about 8/1000th of an ounce. If we were going to compute a test statistic here, what would it be? Well, one thing you could do is take the advertiser at his word. The manufacturer of the cereal says there's 12.8 ounces in a box, so why don't we take a null hypothesis that the mean in the boxes is indeed 12.8 ounces. This would be the mean over all cereal boxes manufactured by this manufacturer. Then we compute a test statistic. That's our t statistic again, because we don't know sigma. So we replace the standard deviation of x bar in the z-score by the standard error of x bar, and we call it a t-score now. So there's just that formula we saw earlier. And here I'm plugging in the values I know, the x bar, the mu value from the null hypothesis, and the standard error that we just calculated. And you find that t is 4.8831. Now remember, the t-score is an estimate for the z-score of x bar. So what we're saying here is that if the null hypothesis were true, if it were true that the average amount of cereal in a box was 12.8 ounces, then our observed value of x bar, 12.8399, is almost 5 standard deviations above where we would expect it, above that 12.8. So this is giving us pretty good reason to doubt the null hypothesis. The evidence points to the true mean as being bigger than 12.8, just because our sample data is so many standard deviations above where we would expect it to be if the true mean were 12.8. We can compare the t and the z-scores if we make an assumption about the standard deviation. And this is what we did in our very first video for confidence intervals. We had assumed for this very data set that sigma was 0.03. So if we compare that assumption to the sample standard deviation in the data, we see that they're fairly close, but not the same. Now, under the assumption that sigma is 0.03, the standard deviation of x bar is this value 0.009487. We can compare that to the standard error of x bar, which is our estimate for the standard deviation of x bar. And it's slightly different, right? 0.008171. So not the same, but that's what we expect since the standard error of x bar is an estimate for the standard deviation of x bar. And the z-score for x bar, assuming sigma 0.3, turned out to be 4.2058. If we don't know that the standard deviation is 0.3, we use S to estimate it, and we get a t-score that's similar but not quite the same. The t-score is 4.8831. In either case, the true z-score or the estimated z-score are both telling us that our observation is really far away from the mean where we would expect it to be. Now, if you understand the concept of a t-score now as just an estimate for a z-score, the next thing to think about is the sampling distribution of that t-score. How does that t-score vary across all possible x bar values as you took, random sample after random sample of size 10? How does that t-score vary? Well, it's actually a theoretical exercise in probability, but it turns out that the distribution of t is quite a bit like the distribution of z. It has a very normal-like density curve, but it is in fact not a normal density. It's a different family of density curves called the t distributions. And we're going to have to keep in mind some terminology here. We actually call it the t distribution with n-1 degrees of freedom, where this n is the sample size. So this idea of the degrees of freedom is going to be important because it plays into which t distribution you use in a given problem. So I denote the t distributions this way. I say the t-score has a t distribution whose degrees of freedom are n-1. And we're going to use these t distributions with the right degrees of freedom when we're doing inference for mu, when we're doing confidence intervals or significance tests, when sigma is unknown. And as I said, that's usually the case in practice. I've got a little Desmos sheet here to give you an idea about the t distributions and to compare them to the normal distribution. So the curve you're seeing right now here is just the standard normal distribution. The normal distribution with mean 0 and standard deviation 1. So that's familiar to us from our earlier work. Now I'm going to plot the t distribution with 1 degree of freedom. So there it is. It's the green curve. So you can see that it has a normal shape, that classic bell curve type shape, but it is not as tall, and its tails are wider than the tails of the standard normal distribution. This is a characteristic of the t distributions. They all have their peak is smaller and their tails are heavier than a standard normal distribution. Here is the t distribution with 2 degrees of freedom. So it's the purple curve you see there. So it again has a smaller peak, but not as small, and heavier tails. Let's remove the 1 distribution. So now you're just seeing the purple curve there is the t distribution with 2 degrees of freedom. Next, the t distribution with 4 degrees of freedom. You can see it's between the t distribution with 2 degrees of freedom and the standard normal curve. I'm going to remove the 2 distribution one now. And here is the t-distribution with 8 degrees of freedom. You'll see that it lies between the t-distribution with 4 degrees of freedom and the standard normal. So there it is. This phenomenon actually continues as the degrees of freedom increases. So now here's the t-distribution with 16 degrees of freedom, very close to standard normal. And here's the t-distribution with 32 degrees of freedom, even closer yet to the standard normal. So this phenomenon is characteristic of the t-distributions. They have more variation than the standard normal. That means the tails are heavier. The peak is lower. But as the degrees of freedom gets higher and higher, the t-distributions get closer and closer, in fact, asymptotically closer, if you've heard that word, to a standard normal distribution. Okay, let's think about how we would do t-distribution calculations on the TI-84. So it's very similar to the normal distribution calculations. If you recall, a forward normal distribution calculation where you're given boundaries on the x-axis and you want to find the area under the normal curve was a normal CDF command. For the t-distributions, it's called TCDF. And you need to give the calculator the lower bound for the area, the upper bound for the area, that's B here, and then the degrees of freedom. And for us, the degrees of freedom will always be the sample size minus 1. Then there's also an inverse normal calculation, where you're given a left tail area under the density curve, and you're asked to find the upper bound of that area. That was an inverse normal calculation when we were dealing with the normal curve. When dealing with t-distributions, it's called an inverse t calculation. And again, you give it the left tail area and the degrees of freedom of the t-distribution, which again are n minus 1. So we'll do an example with those calculations here shortly. In fact, let's do one right now. Let's do a significance test now in the situation where sigma is unknown. So, chocolate-coated sugar bombs are a kind of cereal that comes in boxes labeled 12.8 ounces net weight. Calvin suspects that the actual net weight is higher than this on average. A sample of 10 boxes yielded an average weight of 12.8399 ounces with a sample standard deviation of 0.02584 ounces. Is this statistically significant evidence in favor of Calvin's suspicion? So here I've set this problem up, and I hope you are Calvin and Hobbes fans like I am. But I set it up to just so we could use the data that we have been dealing with so far in this lecture, the weights that we've already been looking at. The basic idea is to go through exactly the same procedures as before, but using sigma as an estimate, using S as an estimate for sigma, and using the t-distribution instead of the normal distribution. So let's see how that works out. First of all, let's frame our hypotheses. Calvin suspects that the amount of cereal in a box is bigger than 12.8 ounces. So that's our alternative hypothesis right there. The null hypothesis is the advertiser's claim that the amount of cereal in a box is indeed 12.8 ounces. What's our evidence? The evidence is the sample data. Again, we have a sample of size 10. We've already looked at that data and computed the mean and the sample standard deviation. The first thing to calculate is the standard error of x bar. So this replaces our sigma of x bar from the central limit theorem. That's S over radical n, and we actually did this calculation before. It's that 0.008171 that we have already seen. The test statistic is our estimate for the z-score for x bar. So since we don't know sigma, we have to estimate using the standard error. So we're using a t-score then, x bar minus the mu value over the standard error of x bar. Plug those values in, and you get that 4.8831 that we've already seen. So that's our test statistic. The next thing we need to do is calculate a p-value. Remember, this is a right-tailed test. Why is that? Look at the alternative hypothesis. It's a right-tailed alternative, right? Mu is bigger than the null value. So the p-value is the probability of all test statistics that are greater than the test statistic we got, which is 4.8831. So that p-value, this would be a forward t distribution calculation because we know the bounds on the x-axis here, and we're trying to compute the area, that green area here. So the p-value would be t-CDF, since it's a forward calculation. Lower bound is 4.8831. Upper bound is infinity, so use 10 to the 99th power on your TI. And the degrees of freedom is 9. Why is that? Because our sample size is 10, and the degrees of freedom is always the sample size minus 1. Now, the tcdf command is available in that same window, the same menu as the normal CDF command. It's the distribution window. So you press, I'm not sure if I can do this, but second distribution, and you see, can you see possibly that? tcdf is item number 6 in my menu. If you've got a newer version of the calculator, it may be slightly different, but it's in that same screen where you find the normal distribution and inverse normal and things like that. So if you use that and plug these values in, use 10 to the 99th for infinity, you'll get 4.3382 times 10 to the minus 4th power. That's 0.000433382. As a percentage, that's 0.04%. So this is a tiny p-value, far smaller than 1%. This says we have extremely strong evidence, p being 0.0004, that the amount of cereal in a box is on average greater than 12.8 ounces. As far as statistical significance goes, this is statistically significant at the 1% level. It's statistically significant at the 1/10 of 1% level. It's highly statistically significant. Let's take a look at a confidence interval calculation, again with sigma unknown. So let's continue with Calvin's chocolate-coated sugar bombs data. What are the plausible values of mu, the true mean weight of cereal in a box? Let's estimate this using a 95% confidence interval. Well, let's collect the ingredients. First of all, our sample data is just as before: the sample size, the sample mean, and the sample standard deviation. Again, we would calculate the standard error. Again, we'd get the same thing. The critical value, remember, for a confidence interval when sigma is known, we call this a z-star, and it's the number of standard deviations in a standard normal distribution you need for the confidence level you desire. Here, since sigma is unknown, we have to estimate that using the t-distribution. So it's the same exact idea, though. The critical value is now a t-value, a t-star value, and t-star is the value such that you get your confidence level, in our case 95%, between minus t-star and t-star in that t-distribution with the degrees of freedom that you have, in our case 9. So in essence, you're looking for the middle 95%, now not of a standard normal distribution, but of the t-distribution with 9 degrees of freedom. And so you reason through that in exactly the same way. The middle 95% would correspond to the 97.5th percentile, right? Because there's 95% in the middle, therefore 2.5% in each tail. So the left tail at t star would be 0.975. So t star is inverse t of 0.975, again with 9 degrees of freedom because our sample size is 10. And You plug that into the calculator, you get 2.2622. I'm rounding to 4 places again. So that's our critical value. And then the margin of error, T star times the standard error of X bar. Remember, this is directly analogous with Z star times sigma of X bar. And you multiply those two things together and you get 0.01848, keeping 4 significant digits here as your margin of error. So the 95% confidence interval for mu is going to be your X bar plus or minus the margin of error. That's 12.8399 plus or minus the 0.01848. And that goes from 12.821 ounces up to 12.858 ounces. So we're 95% confident that the true population mean weight of cereal in a box of chocolate-coated sugar bombs is between 12.821 ounces and 12.858 ounces. In summary then, realistic inference, when sigma is unknown, really just has a few basic ideas. We use S, the sample standard deviation, to estimate sigma. We use the standard error of X bar to estimate the standard deviation of X bar. And we use the T distribution with the appropriate degrees of freedom to compute critical values for a confidence interval or p-values for a significance test. And other than that, everything stays pretty much the same. All the properties of confidence intervals and significance tests that we've discussed before remain the same. And the relationship that we discussed in our last video between confidence intervals and two-sided significance tests remains the same. Just the details of the calculation have changed. But those details are important because otherwise, if you use the Z distribution, the normal distribution, when sigma is unknown, the answers you get out are going to be very inaccurate. They're going to be basically garbage because the Z distribution, the standard normal, assumes that sigma is known. When sigma is unknown, we have to go to the T distribution. So I hope you found this helpful. There will be a homework out there a little bit later tonight. It'll be Tuesday, that's April 8th at 11 p.m. And as always, let me know if you have questions, comments, or concerns. I'm available for online office hours. We could do FaceTime, Zoom, whatever is easiest for you. Let me know if you would like to do that. And in the meantime, stay healthy, stay sane, stay connected, and we will see you soon. Take care.